Beneath the picturesque landscapes of the Pacific Northwest lies a silent and deadly threat, an earthquake waiting to strike. It originates from the subduction zone where two tectonic plates collide. But how does this slow-moving disaster become a sudden and catastrophic event? How does it go from a silent threat to an actual danger? Join us as we delve into the heart of the matter, exploring the process behind this geological time bomb. You might be asking, what is a subduction zone? Imagine the Earth's outer layer, not as one solid piece, but as puzzle-like plates that fit together but also move and shift independently. These are tectonic plates. The area where these plates meet is known as a plate boundary, and at convergent plate boundaries, like the one beneath Mount Rainier, the plates collide. Here's the twist. One plate, the oceanic plate, is denser than the other, the continental plate. So instead of the denser plate simply sinking down, it gets pushed under the lighter plate, hence the term subduction. This process, however, isn't smooth or instantaneous. It's more like shuffling a deck of cards where the cards represent the rocks of the Earth's crust and the denser oceanic plate gets pushed under the lighter continental plate. Now, let's focus on the Pacific Northwest, specifically the region known as the Cascadia Subduction Zone. This zone stretches from Northern California all the way to British Columbia, Canada. It's here where the Juan de Fuca microplate, yes, it's that small, meets the North American plate. And just like our card analogy, the denser Juan de Fuca microplate is being pushed beneath the North American plate at a rate of about 2 inches or 5 centimeters per year. This might seem like a snail's pace, but remember, we're talking about geological timescales. And over millions of years, this slow and steady movement has created some fascinating features. For example, the Mariana Trench, the deepest part of the ocean, was formed by the subduction of the Philippine Sea Plate beneath the Okhotsk Plate. But hold on a second. Why are we fixated on the Cascadia Subduction Zone? Well, because this region is home to some major cities, including Seattle, Tacoma, and Portland. And lurking beneath the surface is a potential giant earthquake. Let me explain. As the oceanic plate gets dragged down into the planet's hot, gooey mantle, it melts slowly. This molten material, now part of the mantle, doesn't stay put. It finds cracks and weaknesses in the rocks above and pushes its way up, creating pockets of magma. Over time, this magma can cool and solidify, turning into igneous rock. You might have heard of Mount St. Helens and Mount Hood. They are examples of volcanoes that have grown thanks to this very process. But that's not the type of mountain we're talking about when we mention Mount Rainier. Mount Rainier is a stratovolcano, a majestic peak standing over 14,000 feet or 4,400 meters above sea level. Its slopes are a mix of ash, lava, and other volcanic materials. But the real action is happening much deeper. Back at the subduction zone, the descending plate carries water with it as it goes down. And as it reaches around 30 miles or 50 kilometers below the surface, the pressure and temperature are high enough to release that water. Now, this water doesn't just disappear. It migrates upwards, seeping between the rocks and gathering in special areas called seismogenic fluids. These fluids play a crucial role in our story. As the water accumulates in these areas, it reduces the friction between the rocks, allowing the rocks on the overriding plate to slip more easily. This slipping motion generates the energy that fuels earthquakes. Picture a group of friends trying to push a heavy box across the floor. If the box doesn't move, they'll exert more force until it starts sliding. But once it starts moving, it slides further. Similarly, when the rocks on the overriding plate get past their sticking point, they continue to move until they reach a new sticking point. Each time they do, an earthquake occurs. And the deeper and more water that's released, the bigger the earthquake can get. This process is the heart of the earthquake engine beneath Mount Rainier. The energy released during these earthquakes radiates outward in all directions, causing the ground to shake and buildings to sway. In the case of a major earthquake along the Cascadia Subduction Zone, this shaking could be devastating for the nearby cities. This region is seismically active, but why do we call the quiet period silent? The answer lies in the nature of these earthquakes. They don't happen regularly, and they don't follow a set pattern. we can't tell exactly when they'll strike, which makes them hard to predict. In fact, the last major earthquake along the Cascadia Subduction Zone occurred in 1700. Scientists know this not just because of geological records, but also because they've studied tree rings in Japan. Some species of trees produce a growth ring when they experience a significant event in their lifetime, such as a fire or an earthquake. And in 1700, Japanese cedar trees recorded a powerful earthquake in their rings. This event, as it turned out, was the same earthquake that shook the Pacific Northwest. Now, you might wonder why we only know about it because of Japanese trees. And that's due to a lack of instrumental records in the Pacific Northwest. That is until the 1960s, when seismographs were set up to monitor the region's seismic activity. What scientists really want to know is whether the 1700 earthquake was a one-off event or if it was part of a cycle of larger earthquakes. If it's part of a cycle, knowing when the next cycle might start could help predict when the next big earthquake will hit. To understand this, we need to look at another subduction zone, the southern segment of the San Andreas Fault in California. There, scientists have identified about 12 major earthquakes that have occurred over the past 8,000 years. By studying the intervals between these earthquakes, they found that there's a roughly 150 to 300 year window for when the next big one might hit. So, while we can't say exactly when the Cascadian earthquake will strike, we do know it won't be in our lifetime. The next major earthquake is likely several hundred years into the future, but that doesn't mean we won't experience smaller ones. Even though the big ones have long intervals between them, there are often foreshocks and aftershocks before and after these major earthquakes. And these can happen much closer in time. For instance, the 1700 earthquake had a foreshock 10 years before and an aftershock 9 years after. Between 1980 and 2004, there were 20 to 4 shocks and aftershocks along the fault. While none of these foreshocks or aftershocks were the main event, they still had magnitudes ranging from 3 to 7.2. So, they can cause noticeable shaking and even damage. We're only in the middle of the 1700 cycle, and who knows what might happen in the coming years. That's why scientists continue to study the region, monitoring the buildup of stress and the intervals of smaller quakes. It's like watching a pot of water reach a rolling boil. Just before it boils, there are tiny bubbles rising, and then suddenly it all boils over. Understanding the quiet period before the earthquake helps scientists better prepare for the inevitable rumble. It's important to note that although Mount Rainier is close to the subduction zone, it's not directly above it. The actual fault line runs about 50 miles or 80 kilometers offshore. However, because the volcano is still within the general area of the subduction zone, its activity is indirectly affected by the buildup of stress and the eventual release of energy along the fault. So, why should you care? Because understanding this process helps us prepare for the inevitable. We can strengthen buildings and infrastructure to withstand earthquakes that might occur. And while we can't stop them from happening, we can lessen their impact. It's like securing your house before a storm. You can't stop the storm, but you can protect yourself from its worst effects. Remember, the earth beneath our feet is always in motion. The quiet periods are just that, periods of calm before the inevitable rumble. And understanding these rumblings is not just for scientists, it's for all of us who share this planet. After all, the Earth story is our story. And as we continue to explore and learn, we discover not just the secrets of the Earth, but our place within it.